It's great to be here. My name is Alex Bolazel, and I'm here to talk about reverse engineering Windows Defender's antivirus emulator. Before I get started, just a little bit about me. I am a security researcher at For All Secure. You may know the company for their victory at the Cyber Grand Challenge 2 years ago at DEF CON 2016, doing automated vulnerability discovery and exploitation. I also do firmware RE and cyber policy at Riverloop Security. I'm a very proud alumnus of RPI and the RPI Sec CTF team, was playing in DEF CON later this week. This is my second time at Black Hat. Previously I presented some work called AV Leak at Black Hat 2016. And before we get started, I do want to say this is my personal research, and the opinions and views expressed are my own, not those of any employers of mine. I want to say this presentation is a deeply technical look at Windows Defender's antivirus and binary emulator. And as far as I know, it's the first conference talk to really look at reverse engineering any antivirus software's binary emulator. That said, it's not an evaluation of Windows Defender. I'm not going to tell you whether this is a good product or not, whether you should use it or not, how effective it is at catching viruses. And it's also not related to Windows Defender ATP or any of the other technologies in the Windows Defender name. We're here talking about Windows Defender Antivirus, the traditional first thing to have the Windows Defender name. So an outline of this presentation, I'm going to go through an introduction, then talk about tooling and process, then my reverse engineering, then a bit on vulnerability research and vulnerabilities inside Defender, and then we're going to have a conclusion. So, Windows Defender is Microsoft's built-in antivirus software built into all Windows systems. And as I said, the Defender name now seems to cover a variety of mitigations and security controls that are built into Windows. And here today we're talking about Windows Defender Antivirus, not ATP, Application Guard, Exploit Guard, or any other technologies with the Defender name. Defender has a huge market share in the AV industry, 8% of Windows 7 systems, and more than 50% of Windows 10 devices. That's because it's my understanding that with Windows 10, Microsoft turned on Defender by default when you install the OS. Defender also runs unsandboxed as NT authority system, meaning that if you have an exploit for a vulnerability inside Defender, you'll get initial remote code execution. You'll also have a privesc up to system, and you'll have an AV bypass because you're running inside the AV, so it's unlikely to flag itself doing anything malicious. It's also surprisingly easy for attackers to reach remotely. I haven't tried this myself, but some friends at Google Project Zero told me that they were able to get Defender to scan binaries by simply emailing them to people who had a Gmail tab open in the background. And then Google Chrome would cache the downloaded file from the Gmail message. It would hit disk, and a mini filter driver would grab it and then go scan it. So it's actually really easy to get into this attack surface. My motivation was, you might have seen this tweet about a year ago, Tavis Ormandy and Natalie Silvanovich at Google Project Zero discovered some great Defender bugs, and I had looked at other AVs but never Defender. So I spent about 4 months reverse engineering Windows Defender's JavaScript engine, which I'm going to talk about just briefly next. And then after doing that, I moved on to looking at the Windows emulator for about 5 or 6 months, and that's what you're seeing here today. Now, Defender has a number of different components and things like that, different plugins, drivers, DLLs, and so forth. Here we're looking at the main, traditional main Defender DLL, mpengine.dll. This is really the main scanning interface for Defender, so it's not doing, say, system call hooking or callbacks or anything like that. It's the main scanning interface that says, given a file, is that file malicious or not? I wanted to talk a little bit about my prior research on Defender's JavaScript engine, which I presented out at Recon Brussels in Brussels, Belgium in February. And some of the themes that I'm going to talk about on the JavaScript engine you're going to see repeated in the Windows engine. This bit.ly link will take you to the presentation. So I found the Defender had a JavaScript engine used for analysis of potentially malicious code that I reversed from binary. I used a custom shell unloader with help from Rolf Rolls. So this was a custom shell we could use to interact with this JavaScript engine, which is not normally exposed to users. And I found throughout the engine that there were AV instrumentation callbacks to inform the engine about actions that potentially malicious JavaScript scripts were using or taking. And I also found that the developers made the choice that seemed to emphasize security at the cost of performance. So the engine is not necessarily super fast like a traditional JavaScript engine, but I found it to be relatively secure. In terms of related work in the AV reverse engineering space, there's only a handful of prior publications. I did some work called AV Leak with some collaborators from my university. We presented that 2 years ago here at Black Hat and Usenix Woot as well. There's also Tavis Ormandy's Defender bugs from 2017 that you might have seen. And Hoxian wrote a great book. But in general, there's not a lot of talk about reversing AVs, and in particular my focus on AV emulators. There's really no prior art. other than there is actually a couple AV industry patents or that great presentation from Bitdefender looking at their emulator from 10 plus years ago. I think it was 2008. So, concluding the kind of background section, let's talk about emulation itself. So, the traditional AV model I think a lot of people think of is this idea of scanning files and looking for known malicious sequences or signatures, such as file hashes, sequences of bytes, or traits of the file. But the problem is that signature-based heuristics like this, using hashes or things like that, are very easily evaded with packed code, novel binaries, and so forth. This has been a problem for a long time. I'm talking 15 to 20 plus years this has been a problem. So about 15 or 20 years ago, the AV industry moved into emulation. So taking potentially malicious unknown binaries and actually running them in a virtualized environment to see what are they doing at runtime, are they malicious or not. And this technology goes by a number of names such as sandboxing, dynamic analysis, detonation chambers, so forth. So an overview of emulation. You're going to take a potentially malicious unknown binary, load it into your virtual memory space for your emulator, begin running from some entry point, and run it until a termination condition such as time, number of instructions executed, number of API calls, amount of memory used, etc. And throughout this process, you're collecting heuristic observations about the malware's runtime behavior, looking for signatures in memory or drop the disk, or anything else you can use to detect malware that you can't detect with a single static hash. All right, that concludes the introduction. Moving into talking about my tooling and process, so how I did what I did. Did traditional static analysis with industry standard technologies like IDEP Pro. Also did some patch analysis with bindiff, so I was able to take multiple versions of Defender and diff them and see what had changed, what had updated. As for example, Project Zero was finding vulnerabilities in Defender. I could analyze and see how Microsoft was fixing them. I found it really nice that Microsoft publishes PDBs. These are debug databases that describe the file, have symbols and structures and things like that. And while I was doing this static analysis, I also did a lot of dynamic analysis, but there's a lot of challenges to doing dynamic analysis of AV engines. Defender's case, it runs as a protected process. You can't debug it even as local admin. You'd have to attach a kernel debugger to a VM in order to actually debug Defender. Introspection can be difficult. The thing is just so complex. When you're looking at emulator, it can be very difficult to analyze the virtual emulated state and the real state and all this kind of stuff from just a debugger. Scanning on demand can be difficult to trigger. If you, for example, have to go into a GUI and select a file and do multiple clicks and drags and drops, that's a pain to automate. And also code reachability can be configuration or heuristics dependent. So in some cases your Defender install will be configured not to use emulation for whatever reason. The solution to this problem is to build custom loaders for AV binaries. And this is not a unique idea to me. Other people like Tavis and Hoxian have talked a lot about the need to do this as well. So I began my work by taking a tool built by Tavis Ormandy of Google Project Zero called Load Library. And what Tavis did was built a PE loader for Linux, specifically tailored to the needs of Windows Defender. This is not a full-featured Windows emulator akin to Wine or anything like that. Just enough to get Defender running on Linux. So loading the P file in and exposing a scanning interface. And I built about 3,000 lines of tooling on top of that in order to enable my research, which I'll talk about. Quick walkthrough of how Tavis's load library tool works. We begin with our Linux MP client binary. This is just binary that's going to do the loading for us. We load and do relocations for mpengine.dll, so it's just a matter of reading the P spec and understanding how to map in a P file into memory, even though we're on Linux. Then we go through the import address table and resolve imports to Windows functions to shimmed out implementations of them on Linux. So for example, a call to create file is shimmed out to a call to fopen, and a call to write file is done with fwrite. And then inside of there we have an emulator, and for now just remember that it has this table gsyscalls. This is basically a table of emulations for various Windows APIs. Outside of there we have our malware binary. We call a function called rsignal with the malware binary as a buffer, and we say, here, scan this buffer of this length. Then we go through some scanning engine selection that will see if they can scan and detect this with, say, static hashes or whatever. If they can't, eventually they'll make their way into the emulator, and our malware binary will get emulated there. Then Defender comes back and says, hey, we found this particular virus. So it's a very simple interface. All you get is a name of virus out. So a quick demo. Let's see scanning with MP client. So here I'm going to scan the eCar test file. This is an industry standard test file for any AV. This is not actually a malicious file, but this is just standard in the AV industry. You scan this and it should say found eCar, not a virus. So we're going to run load library mp client and scan ecar.com. And we'll see Defender comes back with a classification that this was threat virus.ecar test file. All right, so that's just the basic standard tool that just does that scanning. And all we get out is a malware name. In addition to just running the engine, I wanted to collect more information on it, such as debugging it and things like that. And I found that debuggers like GDB on Linux were just a little too low level for what I wanted to do, the amount of introspection I wanted to do, the amount of complexity I was dealing with. So I ended up using a code coverage analysis tool called Lighthouse, which was developed by Marcus Gossadam of Ret2 Systems, who's also a fellow alumnus of RPI-Sec and RPI with me. And what Lighthouse does is run a given binary under Intel PIN or Dynamo Rio instrumentation, then emit a file that has some coverage information which you can then load into IDA Pro, and you can visualize what basic blocks were hit during execution. And I found this to be a very useful tool throughout my reversing, and I'll show some examples of that as I go through. I did find it kind of funny. Halvar Flake, really great reverse engineer with Google Project Zero, gave a keynote about challenges in reverse engineering and actually pointed out that collecting coverage traces from Windows Defender itself, and this particular DLL we're working with, is very difficult because of the fact that it runs as a privileged process. Okay, moving into talking about my reverse engineering itself. First up, we're going to talk about the engine startup and initialization. Very quick overview of that. So Defender's R signal function provides an entry point into Defender scanning. You give it a buffer of data, and it comes back with a classification of the malware. Was it malicious? What is it? And what's its name? That's what we saw with the eCar test file example. As I said, Defender uses emulation to analyze potentially malicious binaries that it doesn't recognize with other less expensive analyses, such as hashing or other heuristics like that. And emulation results are also cached, meaning if you try to scan the file twice over, the first time you scan it, the result of the emulation will be cached, say for example by an MD5 hash or something like that, and it won't be emulated a second time unless you fully reinitialize the engine. Or there are some Microsoft kind of features, a way of doing that, enforcing re-emulation. Emulator needs to be initialized by, say, allocating memory for the emulation, initializing various objects and subsystems. So this is all implemented in C++, so you have to emulate or build up various C++ objects. Then the binary to be analyzed has to be loaded, relocated, resolving imports, and so forth. And you'll actually see here on the right side of my slides some examples like they are looking for, say, a suspicious section size, a suspicious section name, section offset, and so forth. They're collecting heuristic observations about the binary during the loading process. And then they're also going to resolve imports to what they call VDLLs. Just like on real Windows systems, you have DLLs. In Defender, you have virtual DLLs that provide emulation of the Windows API. And you'll also see things like they need to set up an image name. So for example, if you are an executable PE binary, your name is myapp.exe. This is obviously something that you could use to write evasive malware that would look for, is my name myapp? And if it is, it would choose not to run. And you can actually see that reflected here in the loading process itself as they're setting up that particular trait of the emulator. Moving into talking about CPU emulation, the very lowest level of the engine, actually emulating the CPU and the instructions that the malware binary is running. So Defender's emulation of CPUs is actually really not emulation so much as dynamic translation. This is very similar to what QEMU or QEMU, the quick emulator, does. You're basically going to lift the x86 code up into an intermediate representation and then dump it down into a sanitized x86. You're rewriting the code so that it's safe and clean and has certain security properties and, say, can't access outside of the bounds of certain buffers and things like that. They actually support a number of architectures. You can do 16, 32, and 64-bit x86, IL or .NET. They can do VM Protect, so the VM Protect packer they can lift and then dump out, or even ARM. And then this subsystem is incredibly complicated. As you'll see some of the control flow graphs, it's just way too much to reverse engineer the whole thing. So I'm just going to give you a broad overview of how it works and then do a deeper dive on, say, the Windows emulation. So we have these architecture to IL lifting functions that take a given code of a given architecture and lift it up into Defender's unique intermediate representation. You'll see here things like ARM, .NET, VM Protect, x86, x64, to IL. And these are massive, hideous control flow graphs that are far too difficult to take on, would take a lot of time to reverse engineer that giant of a switch case. And basically what they're going to do is grab an opcode and then emit IL bytes accordingly. And you can kind of see this process in the bottom right, as for example, a x86 push instruction maps to 13 in the IL. And ILs are so popular right now, and everyone loves to use them, but Defender has been using this for at least 15 or 20 years, which is really amazing. In addition to just simply lifting the IL lifting an architecture up to an IL, you can do IL emulation in software. I didn't ever observe the IL being emulated in software during my research. I haven't verified this, but my hypothesis is this is so that the Windows Defender developers can support non-x86 architectures, so they don't have to write a JIT engine to JIT from IL down to ARM or IL down to some other architecture. They can just JIT to x86, and if they ever want to run on ARM, they could just compile their software emulator for ARM or any other architecture, and it should just sort of work, albeit slowly. And then we have the IL to x86 JIT translation, which is taking the IL code and then dumping it out into the sanitized x86. And you can even see how this sort of works here, for example, with the LEA instruction. The opcode in x86 for LEA, which is a load relative address, is 8D. And you can see them here constructing the LEA instruction where they're taking 8D and then masking off with a register that would indicate the particular registry you want to LEA into. And you can see that here in the circled red boxes. And then architecturally unique or difficult to emulate or difficult to lift instructions, such as, for example, CPU ID, are handled by calling directly into software-bound emulations of those instructions. And you can see here on the left code that's actually generating a call into a handler function. So here they need to get a pointer to the handler function, a function pointer, and then they're going to generate out here, you can see in these immediates here, moving the appropriate registers, and then actually generating a call to the immediate value to call the register handling that unique architectural event. Microsoft did document this in a 2005 paper published in Virus Bulletin. Recommend checking that out if you're interested. So as I mentioned, there are architecturally specific emulation functions for unique instructions like CPU ID or an ARM QAdd or SM lol, all these kind of strange unique instructions that don't cleanly map up to the IL. So they're going to use these functions to emulate those instructions. I have an example here of the x86 CPU ID instruction, which is emulated here. And here I have like a malware binary that does movie AX, 1000, whatever, and then CPU ID. And using Lighthouse, we can visualize the basic block coverage when this particular binary is run, and we can see that we hit these basic blocks. And here on the comparison of the same immediate, we take the forward branch and hit push 3 and so forth. So this is an instruction that's not emulated with JITting out of the code. Now to talk about some instrumentation, after we've covered the basics of the loading and the CPU emulation, we need to talk about how I did some of my research with some instrumentation before going further. So, as I said, there's very little visibility into the engine. It's difficult to introspect into it, difficult to debug it. When you run the Defender, all you get out for output is the name of a virus that was identified. The solution that I came up with was to give us a malware's eye view. So to hook functions inside Defender that when malware calls them, it can pass data out to the outside, and in turn, the inside of the engine can pass data back into the inside, and we can have a two-way communication with the malware inside. So I want to talk about how that works. So remember, this is the original diagram of Tavis Ormandy's load library tool that I showed you, where we have here all this kind of stuff, and in particular the gsyscalls call table, which is a table of function pointers for functions that are called when various Windows APIs are called inside the emulator by the malware. And I modified MB Client with about 3,000 lines of code, and in particular I hooked the gsyscalls table and replaced Defender's implementations of various OS API emulations like output debug string A or winexec with my own function pointers. So let's see what that looks like. So for example, Defender has an emulation of output debug string A. That's very simple, just peels a single parameter off the stack and bumps the time in the emulator. I can go here and I can find offsets to the various functions inside Defender, and I can then set hooks by overwriting that memory inside the Defender binary. And that means that when output debug string A is called inside the emulator by a malware binary, our function pointer is called instead and our emulation is invoked. So here's the original output debug string A implementation in the top right, and in the center of the screen is my implementation of this function. Let's walk through this. At the top we have our declaration. There's a large structure called a PE_vars_t that's used throughout Defender. It's large and we kind of treat it as an opaque pointer. We don't actually have to manipulate it directly. We use Defender's programmatic APIs for doing that, to interact with it. So I just declared it as a void pointer. Then we have this, in Defender we have a templated structure called parameters1 arg. This is basically a structure that stores a single parameter to the function. So we declare our own array of uint64s to be the parameters array. Then we use a function inside Defender that pulls a single parameter off the virtual stack, meaning they're going to go into the emulated state, read the ESP and EVP registers, and calculate according to where they're being invoked from and everything, and actually pull off the 4-byte parameter from the stack passed to this function. And we're going to use their function to do that for us. So we have to resolve the address of that function. We just call directly into it with the PE_vars_t structure, and we'll get a 1 parameter back. And that parameter is simply a virtual address inside Defender's emulator. So it's actually a pointer, but it's not a real pointer that we can dereference. It's just an address in this virtualized memory space sitting inside our engine. Then we use a Defender function called getString, or PE_getString, that will take that virtual address and translate that into a real pointer that we can actually manipulate with native code. So we're going to do that. We're going to call into that Defender function for doing that. And now we have a string we can simply print to standard out. So this sounds like a lot, but let's see it in action with a quick demo. So remember previously I showed you just a very simple example of just calling ecar test file. Here we're passing in a binary that's going to say hello defcon when it's run. Or I guess it should say hello black hat. But basically we have a binary, a Windows binary that I called defcon.exe, and when I scan that binary, it goes inside the emulator, calls output debug string A with hello defcon, and then output debug string A with this is a live demo. Let me run it with more debug stuff, and then we can see what the emulator engine, what it saw inside. Sorry. With the more debug stuff, more debug output, we can see the exact offsets and parameters, and we can see the exact some of the API calls, and we can see that the virtual address was 43228. It says hello defcon, then the next call is 430, whatever this is, and we can translate that out and print the standard out. So that gives us a view inside the engine. Now it's great that we can just say print out strings to standard out, but how about doing more? We can actually use this to observe what's going on inside the engine as well. So I have to build this binary, as I said. It's not as easy as you might think to just always get emulated consistently. It does take massaging the linker and your compiler in order to create binaries that are consistently emulated, because Defender has a lot of heuristics that it uses to determine if it can or emulate the binaries or not. At the end of this presentation, I will release some code for your own binary that you can put inside the engine and have it go and run. Okay, so we have now established the basics of how our code is loaded, how it's run, and then how we're able to observe what's going on inside the emulator. So now to get to the real meat of the presentation, let's look at the Windows emulation routines that are now exposed to us with this kind of I/O mechanism. So first off, we're going to start off by talking about the user mode environment inside Windows Defender. So Defender has a virtualized virtual file system, just like a real file system. So this is inside this virtual emulator. Your malware can interact with the file system. And using our file system, using our hook function, we're able to dump the entire file system, which I'm going to demo here. There's about 1,300 functions, or 1,300 binaries rather, on the file system. And here we're just running through all those files on the file system and just dumping them out. I'll run that one more time. You can see here, basically our binary is going inside the emulator, enumerating all the files in the file system, and then just dumping them out with our hooked binaries. Now I can ls the dumpfs directory, and we can see all these different binaries that we pulled out. And there are, I think, about 1,500 of them or so. Mostly they're fake executables, but you'll find a handful of other things, like these unique goat files. I found this file that just says the word goat thousands of times over. With this name AAA touchmenot.txt, I had heard this term goat file before. It's kind of an AV industry term for like a sacrificial file that's used for malware to infect or mess with. So in this case, they created a file AAA touchmenot, Presumably, if your malware touches that file, that might be an indicator that you have a malicious binary or something like that. I didn't go in and necessarily try to understand that exact relationship, but it's clearly, kind of an insider joke for the programmers that put the word goat thousands times over. We'll also find fake config files, clearly written by programmers with comments like blah blah. So again, if your malware goes in and say reads this file, that might be a heuristic indicator of malicious intent. We have a virtual registry with thousands of registry entries, with unique entries like for things like World of Warcraft. So again, maybe you have a malware binary that looks for the World of Warcraft registry entry because it wants to, say, steal your login creds to World of Warcraft. This is a way that the Defender developers could detect that is indeed that kind of malware. If they see it doing a reg open key on the World of Warcraft key, that might indicate that it's looking for World of Warcraft binaries, for example. We also have virtual processes inside the emulator, and these are not real processes. They're just names sort of returned in this order. So there's no actual other processes running. There's no IPC or any of the full-on facilities a Windows system would provide. But when you do a process enumeration, which is a fairly common thing for malware to do, it'll give you this list of fake processes. I've highlighted in yellow at the bottom myapp.exe, which is our binary. Then we have, beyond just the user mode environment, we have user mode code inside the engine, which provides emulation of simple Windows APIs. Now, in the real Windows API, there are generally two types of Windows API functions broadly. There are those that are going to stay inside user mode and do things like manipulating a string, returning a hard-coded value, and so forth. And there are those that end up resolving into a syscall. For example, those that write to a file on disk, open a socket, interact with the registry, and so forth. Those actually resolve to a syscall where the kernel has to service this request. In Defender, these are analogously implemented with functions that stay inside the emulator and those that trap into native emulation. And these are called VDLLs inside Defender, the DLLs that provide this functionality. My presumption is that's virtual DLLs. Because these are just regular DLLs and the RP binaries, once I extract them with our file system dumping code, which extracted the 1,500 functions or so, or binaries that are on the file system, we can pop them to IDA and reverse them, which is really nice. So reversing these, what did I find? I can go through that. For the simple in-emulator DLL emulations, we'll find unique reimplementations of Windows API functions, for example, get username A. And in this case, get username A returns a hard-coded string of John Doe. This is something you could obviously use to detect Defender. You could say, if I see the name John Doe, I know I'm running inside Defender's emulator. By the same token, if you ask for the computer name, with get computer name EXA, it'll say HAL 9000, so obviously a reference to 2001 A Space Odyssey. And again, this is something you could write malware that looks for the username HAL 9000 and knows it's running inside Defender. And this is obviously not how get username A or get computer name works on a real Windows system. But these functions are simple enough and they just return a simple string that they can be run inside the emulator, inside that dynamic translation context, without ever escaping into, say, a native emulation of that function. We'll also see things that return simple hard-coded values or just grab a value off the PEB. Lots of functions that are too complex to be implemented with full-on emulations are simply stubbed out. So RPC enable WMI trace is just going to do an exit process -1. RPC exception filter just returns 0, and so forth. So lots of functions that malware may call but may not be expecting them always to succeed are just shimmed out with very simple limitations that just return 0 or -1 or whatever hard-coded value. We'll also find more unique strings. For example, another DLL. There are many DLLs, and I can't show all of them here, but looking at WS232, I thought this was really interesting, seeing these unique strings and German IP addresses and German websites. Presumably, maybe a German developer developed this or something, but again, these are all traits that you could write malware that looks for them and uses them to detect that it's running inside Defender. So we've talked about the simple emulations, those that return simple hard-coded strings or -1 or 0 or whatever hard-coded value. There are also more advanced emulations that require those that on a real Windows system would go into the kernel. In Defender, they trap out to native emulations. So we're going to talk about the user kernel interaction and how the analogous sort of to the syscall instruction, the analogous process is implemented inside Defender. So Defender's native emulation is implemented with a unique hypercall instruction called API call. The bytes of the opcode are shown there, 0F, FF, F0, and then a 4-byte immediate. This is obviously not a real x86 instruction. But inside Defender, as we're running our malware binaries, the API call instruction is used to trap outside of this dynamic translation context. So as the dynamic translator sees the API call instruction, it will then step in and then basically transition from this this emulation of the jittered x86 code. It'll call directly into an emulation routine that provides emulation of that function. So these are for more complex functions. Those on a real Windows system would require going into the kernel. So for copy file W worker, I have an idle disassembly that shows them do an API call over to kernel32 copy file worker. As soon as the dynamic translation, the interpreter for this x86 code that's being lifted to VIL, as soon as it sees the API call, it brings us over here to mpengines function, kernel32 copy file W worker. This mechanism, this is the sort of functions that we hooked when we hooked output debug string A, where these are translating into a function inside mpengine.dll itself that provides emulation. So then there's a gsyscalls table. This is the table of 119 functions that provide emulations for these unique and difficult and complex to emulate routines. So they're all stored here in the table, which has a function pointer to the emulation, as well as a CRC32 of the DLL name and the function name. And this is where we plant our function pointers when we're hooking up debug string A and other functions. So an example of how this mechanism looks like, what it looks like in implementation. Inside Defender's virtual DLLs, inside the virtual file system, they have an emulation of kernel32 output debug string A. It's going to do some things like, for example, check was output debug string A called over 900 times. Maybe you have malware that just repeatedly does output debug string A and they want to know that. So they'll keep a count of how many times it was called. Then they're going to ultimately resolve down into a call to API call kernel32 output debug string A. And this is a function that has here our API call instruction, 0f, ff, f0, and the 4-byte immediate specifying kernel32 output debug string A. And when the dynamic translator sees that, it's going to then transition into providing that emulation for us. So then we reach the native emulation function. This is the function that we hooked when I was showing you output debug string A onto standard out. So we can go through the gsyscalls table and enumerate the functions that are done with or provided native emulation by Defender. And you'll see here add through API 32, kernel 32, and so forth. The ones that are highlighted in yellow are unique to Defender. These are not functions found in a real Windows system. So for example, they have some backdoor debug functions, administration functions, function relating to malware signatures, and in NTDLL, they have a number of functions relating to low-level access to their virtual file system that has the VFS prefix. All these native emulation functions take a large parameter called a PEVARST. It's about a 0.5 megabyte large structure that contains everything about a given emulation context. So it's gonna have your time, all the DLLs the binary is loaded, various heuristic observations about the binary, pointers to the virtual address space, just everything you need to know about a given emulation session. That big single blob of code, or rather of data, is passed into every native emulation. And then programmatic APIs are used to, say, retrieve parameters. So they're going to go in and manipulate the virtual stack. They're used to manipulate virtual memory, get and set registers, get and set and change memory, and even change things like the CPU tech count and the time inside the engine. Virtual memory can be interacted with an API similar to that found in the Unicorn engine or any other sort of programmatic emulator, where you can map in memory from a virtualized memory space, translate that to a native memory you can interact with and touch, and then a number of utility functions and wrapper functions provide easier ways of doing common operations like writing a single byte, reading a single byte, a D word, a word, so forth, various sizes of memory, or doing things like reading a virtual string from the emulated environment. So we've now talked about the mechanism used to trap from inside the emulator to the outside for complex emulations. Let's talk a little about the internal emulation of the Windows kernel and the NT kernel facilities. So Windows kernel facilities are emulated with native code. So these facilities include the object manager, process management, file system, the registry, and various synchronization primitives. This is just like you would find on a real Windows system with the NT kernel. So first off, we have the object manager. This is part of Windows that whenever you access a handle, work with a handle, it's going to pass through the object manager. So handles can be things like processes, files, registry keys, mutexes. Any sort of system resource that you can manipulate with your process has a handle assigned to it. And in a real Windows system, those are stored inside the object manager. Defender supports 5 types of objects, which I've shown here: file, thread, event, mutex, and semaphore. And inside mpengine.dll, there is a virtual object manager to provide a software-bound emulation of this traditional Windows kernel facility. This is done here in mpengine.dll for malware being emulated inside the emulator. As I said, there are 5 types of object with emulations provided by Defender, and they all actually, on the back end, are implemented with C++ classes and subclasses, where they all inherit from a common mpengine object manager object class. You then have things like a file object, which has unique traits like an mfile handle, access mode, share access, and so forth, or a mutex, which is an mutant object, and that is going to have unique traits like was it abandoned and what is the wait count on that object. And then these are all stored in this basically a big hash map in Windows Defender and accessed programmatically through the object manager. The object manager is interacted with by Windows API emulations. So for example, in NT open mutant worker, they are going to open an object, so they're going to go into that hash table and try to retrieve the appropriate handle that the malware being emulated tried to interact with. Or if they want to, say, set information for a file, they're going to pull back a handle and they're going to specifically check, I want a file object. So if you pass in a handle to a mutex to NT set information file worker, that call will fail because it's not a file object. And the object manager is going to manage that and keep track of state and type of different objects that are passed into it. You'll also see unique things like the current process handle is in Windows a pseudo handle. It's not a real handle necessarily in the object manager. In Defender's case, it's emulated as hex 1234. So this is a trait you could use to write malware that looks for hex 1234 and knows it's being emulated inside Defender if it sees that unique value for its own process handle. We also have a virtual file system. So this provides basically software-bound emulation of a file system. It's all done on the heap in Defender, so there's not a real file system with a real disk or anything like that. This is just sort of allocated memory on the heap that stores these virtual files you can write to, read to, interact with, and so forth. There are these kind of backdoor, lower-level APIs for interacting with the file system with the VFS functions. These are used by emulations of the low-level NT APIs for interacting with the file system, but they're also exposed by Microsoft inside the engine, which is something I'm going to talk about a little bit later, how there's some vulnerabilities that manifest through these being exposed to the user, or rather the malware running inside the emulator. Finally, moving into talking about AV instrumentation. Throughout the engine, we have these internal functions that I mentioned that are accessible through the API call hypercall instruction, and they do things like queue up a file for scanning, alias memory inside the emulator, and most interestingly, report malware behavior to inform detection heuristics. So we're going to talk about that. So inside these kind of user mode emulations of various Windows API functions, there are lots of calls to MP report event with various values. This is basically reporting that the malware inside the emulator took a particular action. So if you call get system directory, it'll call MP report event 12331. So if you have some signatures that say, I'm looking for a call to get system directory and then to load library and then to this and then to that, you want to know the sequences of API calls that are called by the malware to inform that detection. So throughout the VDLLs that provide emulation of the Windows API, Microsoft has woven in these calls to MP report event, reporting out to the mpengine.dll, the larger sort of native code, what particular APIs the malware inside the emulator is calling. And it can also pass out strings. You can see things here like if you do a create process and you create it suspended, maybe you're doing process hollowing, so they will pass out the string create suspended to inform Defender that this is a particularly potentially malicious action, particularly sketchy, something you really normal software might not do. More MP report events on things like get file size or get drive type A, again, woven throughout these emulations of various Windows APIs. They're informing Defender about sort of heuristic detections. And one example of this, kind of concrete, very interesting to look at, is, as I mentioned, we have these emulations of various other processes running on the system. And you'll notice that the names of antivirus processes all are in the 700 range. So Kaspersky AV, avp.exe, fsave is fsecure, Norton.exe, mpengine, that's the Defender itself, Outpost, and so forth. They're all in this 700 range as far as their PIDs. These are not, again, real processes. This is just an emulation of these processes being present. It's just a hard-coded value. But you'll notice when you call the terminate process API, if you pass a PID in the 700 range to that function, they will call MP report event with a unique value and say AV. So that's probably a strong indicator that you're malware and you're trying to go and terminate AV processes. So they want to know that you are not just trying to kill any process, which is itself maybe an indicator of malicious intent. You're trying to kill an AV process. That's particularly bad and malicious. So they'll inform that, that part of Defender that you're trying to kill an AV. We also have a function called NT control channel, which provides sort of backdoor administration of the engine. And this is something that Tavisormity was abusing. This is basically, it seems like for developers to manage and debug the engine. So from inside the engine, you can do things like change memory, you can change various heuristics for detection, you can rewrite microcode that's used for emulation of various x86 or otherwise instructions, you can modify register state, you can get the exact version number of mpengine.dll. This is all exposed to malware inside the engine. Kind of interesting, and presumably just sort of a debug feature. I went and reverse engineered the 32 options that this function provides, and you can see them here. So that concludes the discussion of reverse engineering. Finally, we're moving into vulnerability research. We're going to start off by talking about some vulnerabilities inside Defender that Google Project Zero discovered. So Tavisormity at Google Project Zero was looking at the API call instruction and found that he could abuse that instruction by calling it directly from his malware. So he would basically create malware with a read, write, execute text section, and then dynamically generate the exact API call instruction he wanted to call with some inline assembly here. And then when that instruction is run over the virtual CPU, it generates a call into these native emulation routines. So this was Tavis's trick for getting into those unique native emulation routines, was just to generate the API call instruction with the right 4-byte CRC that's required to reach them. So then Tavis looked at the NT control channel interface, which is again that sort of backdoor administration interface. It seems like for developers to administer the engine, and found that when he used option 12, which is to load new microcode, there was this loop, and then the count, which is the number of entries provided in this structure with new microcode, it's user controlled. And you can pass it an arbitrary amount of new microcode, and you only have a statically allocated buffer to store that new microcode, so you get a nice linear buffer overflow. Microsoft patched this with a check that only 1,000 entries are passed in through this microcode interface. Also, Tavis looked at the VFS subsystem and found that the VFS write function, which is a lower level API below NT write file, providing emulation and access to the virtual file system. If you began by writing to a file with nothing, with 0, basically you could have a heap allocation inside the real engine. That would basically be like empty there. And then when you do another write, you could have an arbitrary heap write, like a linear overflow on the heap. Very bad vulnerability, vulnerability that's pretty easy to exploit. It seems like you could also get arbitrary read as well in the heap. So this was very bad, that you could reach this internal API from malware inside the emulator. So then Microsoft patched these vulnerabilities out, and I started looking at the API call instruction and the mechanism provided. I was actually able to get around some of the mitigations that Microsoft added. So Microsoft added this check to isVDLL page, which is used to, whatever the API call instruction is invoked, it's going to check, is that API call instruction coming from the malware text section or is it coming from a VDLL? This prevents you from using Tavis's trick of just generating the API call instruction yourself. So because I dumped out the VDLLs, I was able to go through them and find the API call stubs inside the VDLLs that provide access to these APIs. And by just bouncing off them in memory, I could again open this attack surface up. I did report this to Microsoft, and they said it's not a trust boundary. It's kind of a common response from Microsoft when people reported vulnerabilities to them that aren't quite, say, an exact memory corruption, but are sort of a logical flaw. So you'll see an example here. We can call output debug string A by simply finding the offset inside kernel 32 where the API call instruction to output debug string A is, and then just sort of bouncing off that with this particular offset. And we can also open these up, these bad debug functions like control channel, again finding the offset to call that function, and we can again call into that sort of backdoor administration interface from inside the emulator. This seems like a pretty systematic sort of design thing that you have to have these API call stubs exposed within the emulator. It seems fairly hard to patch out a vulnerability like this. I'm going to skip over the quick demo of that. But basically, I think this, it's not quite a memory corruption, but does open us up to controlling and manipulating the engine, and also lets us access an attack surface with a known history of vulnerabilities, as Google Project Zero has demonstrated. And you can do all sorts of weird debug interface things with control channel. Finally, I want to talk a little bit about fuzzing. So I was able to build a customized fuzzer to fuzz the Windows Defender native emulated APIs. Again, this is sort of the attack surface in the engine. If you can hit those native APIs from inside the emulator, you could break out of it because this is native emulation of these functions. This is akin to doing a privesc by hitting a Windows kernel syscall. So I took MWR Labs' OSX syscall fuzzer, which just generates some values. This is not anything fancy like AFL, no coverage, no instrumentation, just throwing random values at Defender. And then I was able to do things like fuzz ntwrite file. I fuzzed a vulnerable version of ntwrite file from an older build of Defender, which Tavis Ormandy had his VFS write function in, and his vulnerability there. And I knew that the Tavis's parameters to ntwrite file were not, or rather to VFS write, would not be accepted by ntwrite file. But I fuzzed the function in order to see if I could reach the same vulnerable code path in VFS write file through ntwrite file. And I was able to do that in about 7 minutes of fuzzing at around 8,000 execs a second. So let me just quickly demo that. So this is sort of running that fuzzer and just throwing these random values at these APIs over and over again. It's going to take a minute to initialize, and here we're just throwing indefinitely. It'll just keep running and running, throwing these random values at these APIs. Potentially we find a crash if we hit one of the native APIs. So that was the demo. Now wrapping up with the conclusion. We covered tooling and instrumentation, CPU, dynamic translation basics for x86, a bit about the Windows user mode environment, and a bit on vulnerability research and how we could fuzz this engine. But there's a whole lot we didn't cover. The Defender is absolutely massive, and there's a whole lot even just in the emulator we couldn't cover in just an hour today. In addition to the emulator inside mpengine, we have things like unpackers, parsers, a JavaScript engine, which I talked about at Recon Brussels, other scanning engines, and a .NET engine. So there's a whole lot more attack surface, 12 megabytes of code to look at. There's also a Lua engine. I want to say broadly, people love to talk about AVs and vulnerabilities that may manifest themselves inside antivirus software, but there's not at all a lot of ground truth at all about AVs, about emulation systems in AVs, or really any other facets of AVs. And there needs to be more research in AVs, I think, before people make these broad claims about how they work. Don't get me wrong, AVs have plenty of attack surface, introduce plenty of vulnerability into your systems, but people love to sort of hand wave at that and just say, well, AVs make you vulnerable, AVs let you get hacked, without actually studying any research or showing that. So I hope more people would reverse AVs, because right now there's just not a lot of publications about them, and I hope I've inspired people to do that and shown that it is possible. If not, it is rather difficult and time consuming. I'm going to release some code later today or later this week, sharing some of the instrumentation I built for Defender, such as the output debug string A hooking, a malware binary, which I have linker settings and compiler optimizations that make it consistently emulated inside the emulator. I've also got an article coming out in Pocket GT Phone 19 describing more of this detail. And that kind of concludes my presentation. I'm going to release slides online. I have over 200 slides I'm releasing with a ton more information because there's way too much that I could just cover in just 50 minutes. So I hope you've enjoyed the presentation. I have open DMs on Twitter if you have any questions, and I guess I don't have much time to take questions, but I'll be happy to talk to people after one-on-one. Thanks very much.